All right, everybody, let's get started. Lecture 2. Although, is it really Lecture 3? Since, again, most of you got me, 5 days a week. I got to say, it's going to be, I don't know how it's going to be for you, but for me, it's going to be a little jarring because this class and 321, they're not alike, in terms of their material and how the classes, the types of stuff we talk about, the lab, in the other class. It's going to be, for me, it's going to be back and forth in terms of, what I'm covering. So, but hopefully, you all get something out of it. Okay, don't forget to scan the QR code, by the way. I did go ahead and get the attendance up to date from the previous lecture, so that's all posted to Blackboard. I mentioned this yesterday in 321, but it applies to you all as well, that you all should have gotten manually added to the OneNote for the class. So that used to be done automatically, but I had done a little digging yesterday, and like I said, I think what's happening is because of Microsoft's decision to no longer support Windows 10 effective October, and because it's in the middle of the semester, for OneNote, at least for this semester, we had to sort of manually add you and whatnot. So I guess just let me know if there are any issues, because we're going to start, or at least I'm going to start using that today, so you should be able to view what's going on in the notebook here in a little bit. Today's lecture, we're going to start getting into structural analysis, and so the way the class works, I have several topics that we're going to discuss, and some of those topics will cross multiple lectures. So, for example, we'll spend 4 lectures on reactions, we'll spend 7 lectures on shear and moment diagrams, but this is the only lecture on this topic. It's one by itself, and we're going to talk a little bit about modeling structures. Remember how we said last time, we're not really analyzing structures, we're analyzing mathematical models that represent structures. So we're going to talk about the tools that we use, which you all have already seen from statics, so it's not like I'm showing you anything that you aren't familiar with. But what we are going to try and do with those tools is we're going to try and classify structures. And classifying structures, really we're trying to answer 2 questions. We're trying to answer whether or not a structure is stable, and whether or not a structure is determinate, or if it's indeterminate. And if it's indeterminate, what is its degree of indeterminacy? And we'll talk about that. You'll understand what I mean after the lecture and whatnot. Everybody get a code? Yep. Okay. All right. Let's pull this up. Okay. So a lot of today is going to be reviewing stuff that you did in statics, and so by that I mean understanding the modeling tools that we use, the types of boundary conditions that we use. There are going to be a couple things that we discussed that you didn't see in statics. You probably didn't deal with internal releases in statics. We're going to deal with that a lot in here, but again, we're trying to assess whether or not a system is stable and whether or not a system is determinate or not. Okay, so let's talk a little bit about modeling systems, the basics. What are the boundary conditions that we more often than not utilize? And then what am I talking about with internal releases? Okay. Okay. So the last time we sort of ended with this. Okay. And the idea is that what we're doing is we're not analyzing structures. We're analyzing these mathematical models that represent structures. Now, I'll just be candid, throughout this semester, I'm probably not going to say that again. Bless you. In other words, when we have a problem, I'll say, let's analyze this structure. Even though we're not really analyzing the structure, we're analyzing a model that represents it. But saying analyzing a mathematical model that represents a structure every single time, that's a mouthful. So that'll be me abbreviating that from here on out. But the goal is to take a system and modeling it, using a system like this. The idea is that we're trying to simplify the problem for our purposes. And remember, our purpose is, let's say here's this, roof truss, and this is the model that we've chosen. Ultimately, we need to know the axial force in these members so we can start selecting members. That's what we're after, okay? As long as we've selected those members and ensured a reliable factor of safety, that's what we're after, okay? So it's okay to apply a model that sacrifices a wee bit of accuracy, but for that wee bit of accuracy sacrifice, we get a lot more simplicity in what we do. That's okay. We do that all the time, okay? So the idea behind what we would do is, let's say we have a bridge here. A bridge is a 3-dimensional structure, okay? And, you know, we look at the structure, we say, okay, really it is these two parallel trusses that are supporting the load. And so what we will ultimately do is analyze each of these trusses independently. You all probably remember the method of joints or the method of sections. We're going to redo that in here, although we're going to do things a little bit differently. One of the ways I kind of like to describe this class is, you know, it's sort of like statics 2. And the way that I like to describe it is we take the techniques and the tools that we did in Engineering 213, and we sort of simplify the tools or the tools a little bit, but we use those simplified tools to address more complicated structures. So we'll do method of joints, method of sections, reactions, and all that, but like one thing you won't see in this class are the letters I, J, and K. We won't be doing any like dot products or cross products or anything like that. So we're sort of dispensing with that in here, but we're then going to be given more intricate structures. So that's sort of the way that it's going to work. But ultimately, we've taken this 3D structure and we've simplified it, here in this case, to a 2D model. And that's often what civil engineers are doing, is they're trying to reduce the dimensionality of a problem to something that we can solve on paper. Because again, as long as we get these forces and we can reliably and accurately predict forces, again, it's not exact, it's a prediction, but as long as we can reliably do that and accurately do that, that's what we're after. Okay? Now, one of the key aspects of one of these models are a boundary condition, okay? Just to make sure we're all on the same page, do y'all recognize where I took this picture? That's between the buildings, right? Okay? So I want to kind of look at these two columns, and you can sort of treat the columns the same way. So I'm looking at these two columns that are supporting the canopy that connects this engineering building to the Weisberg Engineering Labs. Okay, and I want to look at the bottom and the top. Okay, and you could look at the bottom and the top here, the bottom and top here. It wouldn't really matter. Okay, now let's take a look at the bottom first. Okay, so the bottom in this image is, you know, for the column, is this column is encased in concrete, right? So there, you know, it's literally all encased there. And if that column is encased into the ground with sufficient depth, I would probably idealize that as a structural engineer as a fixed boundary condition. Now, we'll talk a little bit more detail about what that means here in a second, but the reason, at least for now, the reason that I would call this a fixed boundary condition is, again, if it's encased deep enough in the ground, that I could assume for the purposes of analysis that this point is restrained against both translation and rotation. Okay, and that's really the characteristics of a fixed boundary condition, is that fixed boundary conditions restrain translation and rotation. So that point couldn't move left or right or move this way, but it also couldn't twist. Okay, whereas if I'm looking at the top, okay, these I-beams that are W sections, we'll talk about that maybe a little bit later, but these W sections that are framing into the top, they're preventing it from moving, but there's not enough beefiness, if you will, in the connection that will prevent the top from rotating. So in other words, the top of these columns are probably going to be allowed to rotate a little bit, but because these are connected, it can't move. Okay? So this is going to be more like a pinned boundary condition. Okay? And a pinned boundary condition is one that prevents translation but allows rotation. Okay? And it's because of the specifics of the connection. And I'm actually going to show you why that is here in a little bit. Okay? But so I think that at least my initial point is that, again, if I told you to analyze this column, okay, I'm just telling you to analyze the column. As the analyst, you kind of need to know what boundary conditions to apply here, okay? And that's your job as the analyst, okay? Now, a more general, though, definition of a boundary condition is that they are the support systems that attach a structure to the ground. Okay, and I'm using that term, the ground, very loosely because it depends on what element that you're looking at. Okay, so for example, let's take this beam right here. Okay, so the ground for this beam is this girder and whatever girder it's connected to over here, right? Because that beam is up in space and it's held in space by this connection and that connection. Okay. So if I was analyzing that beam, I would treat my boundary conditions as here and here. And then whatever force I get right here when I analyze this girder, I get a force here and a force there, okay? So it's sort of like a hip bone connected to the leg bone type of approach. And that process is called a load takedown. We'll probably talk about that near the end of the semester, about how to do that. But my key point here is identifying what those boundary conditions are. You got to know what those are in order to perform structural analysis. Now, the three most common boundary conditions that we deal with as structural engineers are pin, roller, and fixed supports, okay? Now, again, these are analytical abstractions, okay? Nothing in this world is perfectly fixed or perfectly pinned, okay? For example, if I look at this connection here on the top right, I would treat that as a pinned support, okay? Because I'm assuming it's not going to resist rotation, and I'll show you what I mean by that here in a second. But it's not going to freely rotate. It's going to resist a little bit of rotation just because of friction and how it's connected, but not enough to be deemed structurally significant. Okay. So in other words, we'll assume for the sake of discussion that this is a pin support. Now, what is the characteristic of a pin support? A pin support will resist translation, but it allows rotation. So like I think a more concrete example of that may be like this one here on the bottom right. That pin support, I mean that element can freely rotate in that direction, but this point can't move left or right, and it can't move up and down, okay? So that is a perfect example of a pin support, okay? Now, from an analysis perspective, we'll say that that has two independent reactions, an independent unknown force in the x direction and an independent unknown force in the y direction, okay? When I draw that on the board, I will draw that with a triangle, okay? I imagine in statics you probably did something similar, okay? I did go ahead and throw, this is what your book does for pin connections. That's the symbol that it uses. So in case you see that in the book, that's a pin support, okay? Now, a different example of a simple support, and I'll go back to simple supports here in a sec, is a roller support. A roller support is sort of like a pin support, but it only has one unknown reaction instead of two, okay? Now, analytically, we don't care, so like if I look at this image here on the left, we don't care if the reaction is going up or going down. It very possibly could go either way. But really the characteristic of a roller support is that it allows free rotation, okay? But it also allows a bit of lateral translation, okay? The other thing is that the reaction is in the direction of the roller. So here in a little bit, probably sometime next week, we're going to be dealing with inclined rollers. And so how would we compute reactions for that? We'll take that problem as well. This is sort of an example maybe of a real world roller, but there are more subtle examples of what we do in the real world. A good example of a roller support or in combination with a pin support is what we do in bridges with fixed and expansion bearings. Has anybody ever heard that term, fixed bearing and expansion bearing? Some of you are shaking your head yes. Maybe if you've done a DOH or DOT internship over the summer. A couple things on that. So first off, if you ever hear me use the term simple supports, a simply supported system is one that has a combination of a pin support and a roller support on opposing ends of the structure. That's what I mean by simple support, okay? So in other words, the ends allow rotation and the structure can't translate laterally. That is a simply supported system. Oftentimes in bridges, we will use a combination. So let's say we have a simply supported bridge. We will use a combination of a fixed bearing and an expansion bearing. And a lot of times the characteristics of a fixed bearing is you have, like girder, plate, bearing, plate, then it goes to the abutment. And you have the same thing on the other end. But the difference is that the expansion bearing will often use a plate with slotted holes, so it allows it to move a little bit and translate. Does anybody know why we use fixed bearings and expansion bearings in bridges? Like, why would we care that one end of the bridge can translate this way? Why would we care about that?
It can expand in the weather.
Exactly right. Thermal expansion and contraction. I mean, think about a bridge today. We talked about this a little bit yesterday. But think about a bridge today versus a bridge in February, okay? The change in length along the span could actually be pretty significant depending upon the original span length of the structure. And so having a little bit of wiggle in the bridge laterally is a good thing, because if you just restrain it, it causes enormous amounts of lateral forces on your abutments and foundations. So having a little bit of wiggle is a good thing. Now your maintenance engineers will get upset because then you get all sorts of leaves and twigs and mud and gravel and grimy things in there, and it causes all sorts of maintenance problems, but it's that or the bridge falls down, so it's a trade-off. This is one of those you don't let perfect get in the way of good sort of things. It is also one of the other reasons why we use a lot of elastomeric bearings. For any of you DOH folks, have you seen an elastomeric bearing before? I'm just curious. So an elastomeric bearing is the device that connects the beam to the abutment, okay? And it basically is a big old pad of vulcanized rubber with some steel shims in there, and it sort of acts like super stiff jello, so it allows a little bit of wiggle under thermal expansion and contraction. So it's a very common, a very popular bearing system these days because they're really easy to deal with in terms of construction, and they allow the movement that we need. So that's me going off on a tangent a little bit, but I can't help it. So, okay, fixed support. Okay, so a fixed support is one that restrains both translation and rotation. Okay, there are once you start to know what to look for, there are some easy ways to identify fixed supports versus pin supports. So in the case of a concrete element, a fixed support is usually the case, like for example, when the beam and the column are cast together. So the beam and the column are all cast as one monolithic unit. You can treat the end of that beam as fixed. One other way that you can see a fixed support, let's say in a steel element, is when both the web and the flanges are connected, okay? And typically in steel design, when we're looking at structural analysis, we sort of think as the web as the element of the beam that transmits the shear, and then the flanges are the elements that translate moment. So if the flanges aren't connected, we sort of think of that as a simple support because it's the flanges that transmit the moment or prevent the rotation. And if the flanges aren't connected, it can freely rotate, hence a simple support. So in the case, like for example, these beams connecting into this wall, you can see that it's the web and the flanges all connected together. I'll probably just draw that as a line with maybe like a little hatch, and fixed supports have 3 unknown reactions, 2 unknown forces, and then an unknown concentrated moment right there, okay? And an easy way of thinking about that is if you have like a ruler or a pencil in your hand, just hold it in your hand, like grip it tight, and then push it down. Not only are you having to keep the ruler up and down, but if you want to keep it flat, your hand's having to twist back a little bit. Like if you put the ruler in your hand and you push down, if you don't resist it, your hand will just turn, right? You have to turn your hand back to keep the ruler flat, right? So your hand is having to twist it a little bit right there. That's that concentrated moment right there. Does that make sense? Okay. Yeah, so like I said, yeah, those flange connections are the ones that transmit moment. Okay. Let's talk a little bit about internal releases. Has anybody ever seen a bridge with a connection like this? You might see that in an older bridge and whatnot. This is what's called a pin and hanger connection. So it's actually fabricated in such a way that it doesn't transmit moment, it only transmits shear. Another more analytical example of that might be something like this. Like if I had a beam and a beam that was connected together, and I only connected the webs, but not the flanges, okay? This would be a connection that transmits shear, but not moment, okay? Now what I'm doing there analytically is I'm creating what's called an internal release, okay? So do you all remember from statics, and I know it's been a while, but do you all remember from statics the idea of a shear and moment diagram? Y'all remember that? So let's just sort of recap that, and we gave this example last time, or yesterday in 321, but if you weren't there, so if I'm sitting here on this table, if I'm sitting right here, if I'm sitting on this table, okay, and you take out the samurai sword. I pointed to you yesterday. So if you take out the samurai sword or lightsaber and you cut through the table, okay, I'm falling down, okay? And the reason why that is the case is because the table right here is resisting shears. It's resisting moments, and it's keeping me upright if I sit right here, right? Okay, all a shear and moment diagram is a plot of those internal forces, those internal shears, internal moments across the span. That's what a shear and moment diagram is. When I install something like a hinge or an internal release right there, what I'm doing is I'm installing a point where I know what the internal forces are at that point. The most common internal release that we will deal with in this class is an internal hinge, okay? So we'll have a structure, and there'll actually be an internal hinge right there in the structure. And we call that an internal release, and later on we're going to refer to it as an equation of condition, because at that point we know what the internal forces are. So if we put an internal hinge in the structure, we know what the internal moments are right there. And the internal moments at a hinge are 0, okay? Now, a couple questions that are very reasonable to ask at this point is, why in the world would somebody put a hinge in a beam like that? Why would you do that, okay? Why would you knowingly place a point on a structure that can't resist any moment? Like, isn't that crazy? Is that a crazy thing to do? Well, that's a fair question, okay? So, let me give you a couple of different answers, okay? Number one, let's take a beam like this. Okay, later on, here in a little bit, we're going to look at a beam like this, and we're going to understand that this beam is one that is indeterminate. But for the sake of discussion, we don't really need to know what that means right this very second. If I were to draw the moment diagram for this beam, it would look something about like this. This is about what it would look like. Okay, so it would have a positive region, then a negative region, then a positive region. Okay, so what's happening in a bridge like this is the engineer is placing those pin and hanger connections about where the moment is 0 anyways. Okay, that's what the engineer is doing. Okay, now, so that's why they're there. But that doesn't answer the question of why they're there in the first place. Okay, so there are two reasons why they're there in the first place. Number one, this bridge is probably hundreds of feet long, and I don't know about you, but you kind of have, like, imagine if this bridge was in West Virginia. The roads are kind of like this. You can't transmit a 300-400 foot beam along roads in West Virginia. You got to break that beam up into pieces and then assemble it on site. So the beam can't come together in one solid chunk. It's got to be spliced together. Okay. But then the question comes, well, why did you do it like this? Why didn't you just use like a full bore splice? Well, number one, this was cheaper. But really this goes back to bridge engineering that was done what I'll call back in the day. And by back in the day, we're talking pre-Bill Gates, okay? You have to understand, today we have computers and Apple Watches and iPhones that can do more math than was even thought possible when these bridges were designed. These bridges were designed using a very manual computer called a slide rule. Like, has anybody heard of a slide rule before? So the math was all done it was all literally done by hand. So this was an analytical trick to make the analysis doable by hand when you're designing bridges in the 50s and don't have computers to do all the analysis, which is why we don't do this anymore. Doesn't mean they don't exist, but from back in the day, but we just don't build bridges like that anymore, and that's why. Okay. Now, the only other thing I'll say, and then we'll move on, is that we will, even though it is 2025 and we have our computers and Apple Watches that can do all our math for us, we will still deal with internal hinges, mainly because internal hinges are an analytical tool that we can use for future analysis. So you'll see internal hinges pop up when we draw influence lines later. But that's like a November topic. But we will see them for that reason. So even though we might not be building them, we do use them as a trick for analysis later on. Okay, Everybody good so far? Okay, so that sets the stage for my real goal for today's lecture, which is structural classification, okay? And in other words, what I really want to answer are two questions. Is a structure stable or is a structure determinate? But I got to explain what those mean, okay? So I'm going to take it back. We're going to take it back to square one, and we're going to talk about statics, okay? We're going to talk about equations of static equilibrium, okay? So I'm getting very general and then narrowing it down a little bit. So in general, a three-dimensional system, if it's going to be in static equilibrium, has to satisfy 6 equations of equilibrium. The 3 sum of forces equations and the 3 sum of moments equations, okay? Now, again, we in civil engineering, oftentimes we will idealize systems as two-dimensional models, so we can take these 6 equations, turn them into these 3, okay? And the magic number for today, if, you know, what was it? This lecture is brought to you by the number 3, okay? This lecture is brought to you by the number 3, and the number 3 is something I want you to keep in the back of your head throughout this lecture, okay? For any structural system in equilibrium, we know 3 things about it. We know that the sum of the forces in the x direction must be 0. We know that the sum of the forces in the y direction must be 0. We know that the sum of moments about any arbitrary point must be equal to 0. Those are 3 known facts, okay? Does that make sense? 3 known facts. Well, if that's the case, let's think about this a different way, okay? So first thing I want you to do is sort of clear your mind a little bit, and I want to look at this problem right here, okay? Does this problem look like a familiar type of problem that you've done before? This is a statics problem, right? Okay. Now, when I taught Engineering 213, we didn't talk about this stability and determinacy stuff. It was just, here's the problem, let's do it, okay? But in here, we kind of have to take a little bit of a step back because, you know, in statics, it's just I'm giving you the problem, you're doing it. But in here, it's a little more higher level. You all are creating the models, right? So you need to understand what you're creating and what you're doing. So we got to think about it in that perspective. How many unknown reactions are on this problem? 3, right? We have an unknown reaction here, an unknown reaction here, an unknown reaction here. Now, I can already see probably some of you are going, well, wait a minute, what's this one? What is this one, by the way?
0.
Now, how did you figure that out?
There are no other external forces in the x direction.
So what you're saying is you used this, right? Everybody with me on that? And the way that we would figure out these two is to use these two, right? Maybe what we would do is sum moments about that point to get this one, then sum verticals to get that one, right? Does that sound familiar? But let's just think about this in general. So I'm using this term unknowns and knowns. How many unknowns do we have? 3, right? An unknown reaction in the x direction and 2 unknown vertical reactions. But how many knowns do we have? What are my known quantities? 3. I know this, I know this, I know this. So in other words, the number of unknowns matches the number of knowns, right? And in this world, the only thing we need to fully analyze this structure is statics, okay? I propose that this, and just so we're clear, this works internally as well, okay? So in other words, if I break out the samurai sword or the lightsaber and I look at the internal forces inside a structure, I have 3 unknowns, an unknown axial force, an unknown shear, and an unknown moment. And again, same story, 3 unknown resultants, 3 known equations. Again, same story. The big point I want to make is that whenever you have a situation where the number of unknowns matches the number of knowns, we have a term for that. We call that system determinate, okay? That's what static determinacy means, okay? It means that the number of knowns matches the number of unknowns. In other words, we can solve that system using just statics, okay? Now, that example that I mentioned a bit ago with the pen and hanger connection, I said that system was indeterminate, okay? If you have too many unknowns, like if you have a structure with 12 different support conditions, okay, and you only have 3 equations of equilibrium, We have a name for that. Bless you. We have a name for that. We call that an indeterminate system. In other words, there's too many unknowns to solve the problem. Okay? Now, what if the flip side is true? What if you had a structure that only had 2 reactions and didn't have 3? That structure is unstable. Okay? And I'm giving you just some definitions now. I'm going to clear up these definitions here over the next few slides. Okay? Now, most of the structures that we analyze this semester are going to be structures that are determinate. Okay? And the reason is, in order to analyze indeterminate structures, you first have to know how to analyze determinate ones. In fact, a lot of the indeterminate analysis techniques that we use are hinged based on determinate analysis first. Okay? So you'll see what I mean as we progress throughout the semester. Okay? Everybody with me so far? Okay. Now, what we're going to talk about in our examples coming up here a little bit is this term which I'm calling the degree of external indeterminacy, or I sub E. And just so you are aware, a little bit later, we will have degrees of internal indeterminacy. Okay? Those internal indeterminacies are going to be a function of, is it a truss? Is it a frame? Is it a beam? Okay? So we'll get to that later. But externally, we're going to treat structures all the same. Okay? Now, what I am doing in this equation, okay, if you want a simpler way of thinking about this equation is unknowns minus knowns. Okay? That's really what this equation is saying. So externally, what are my unknowns? The support reactions. The forces that keep the structure in equilibrium. What are the known quantities? Now, I'm saying the known quantities are EC plus 3. So first off, why is the number 3? Because there's 3 equations of statics. That's exactly right. Remember I said this lecture is brought to you by the number 3, right? There are 3 equations of statics for 2-dimensional systems. So there's going to be 3 knowns. Okay? What is this EC? EC, so the definition that we're using is equations of condition, but really all that is the number of internal releases. How many hinges are in the system, and so on and so forth. Okay? Now, everybody with me so far? Now, this slide has a lot baked into it. Okay? Let me go through these notes. If you get a negative quantity for I, the structure is unstable, just point blank. Okay? And I'll show you some examples of what I mean here in a second. Now, if IE is non-negative, the structure should be stable. And I say should be here because I'm saying a non-negative value of I doesn't guarantee stability. Okay? We'll talk about that here in a second. But if I is 0, the structure should be determinate. And if I is greater than 0, it should be stable and indeterminate. Okay? So I guess the biggest question is, Dr. Mike, could you please clarify what you mean by this whole should be thing and what's the deal with stability? Okay? So I will talk about that here in a second, but does everybody have all this? You want me to stick around here for a second, or y'all got this written down? You got just a second. I'm saying. Nah, you're fine. You're fine. Okay. All good? Okay. Now, first off, we'll get to stability here in a second, but and more rigorously define stability. But let's look at some basic examples. So let's take a look at this beam right here. So this beam has 2 roller supports. So if we just calculate I, we get I equals 2 minus, there's no internal releases, so 0 plus 3 is 3. 2 minus 3 is negative 1. I propose that that structure is unstable. Okay, it's just unstable. Whereas this structure, we'll say it is stable, and we'll say it's statically determinate. Now, for all of these on this slide, there are no internal hinges or anything like that, no releases, so E sub C is 0. Okay. Now, in the case of this beam down here, this has a fixed roller, so how many reactions do we have? We have 1, 2, 3, 4, 5. So we have 5 reactions, 3 equations of equilibrium. We have I as 2. So this structure is stable and it is indeterminate. And whenever you have an indeterminate structure, it is common to say that it is indeterminate to the 2nd degree, or to the 5th degree, or to the 47th degree. And the reason is, the higher that number, the more difficult the analysis. Or actually, difficult's not really the right word. The longer the analysis, the longer that it takes to do. So a statically indeterminate structure to the 1st degree, it's kind of a pain, but you can probably do it by hand. 1 to the 50th degree, break out a computer program. Otherwise, it's going to be miserable. So, does that make sense? Do these, at least calculations, make sense? Hopefully they're not too challenging. Now, I do want to focus on this structure up here. I'm proposing to you that it is unstable, okay? And when I say unstable, I'm saying it right now on this slide based on the math. I is -1, so it's unstable. I'm saying no matter what, if I is negative, it's unstable. Let's ignore the math for a second. Can somebody give me a more general answer? Why do you think this structure is unstable? Ignore the math. Why is this unstable?
There's no opposing forces.
Opposing forces which way?
Downward.
Well, I guess what I'm getting at, isn't this a skateboard? It's a skateboard, right? So if I had a skateboard, imagine that I had a skateboard sitting right in front of me. Okay, if I stand on the skateboard vertically, I mean, assuming I can keep my balance, it'll sit still, right? But what if I take the skateboard and I just boop, tap it? What's it going to do? It's going to freely displace. Is this going to freely displace if I tap it? No, because this reaction is keeping it pinned back. No pun intended. It's literally a pin connection, right? Okay, so stability is all about unrestrained kinematic displacement, okay? And that's what I mean when I say stability is not guaranteed if I is non-negative. Let's do some quick mental math. What would the I value be? Well, I'll put it up here. What would the I value be for this? It'd be 1, right? Because there's 1, 2, 3, 4 reactions. 4 minus 3 is 1, right? But is this structure stable? No, because boom, it could go, right? It could very easily just translate, okay? This structure is unstable because under a lateral force, it will freely displace. And it will not return back once you remove the loads. And that is what it means to be unstable, okay? Now, the 2 checks, if you want a rigorous check, the 2 checks for a structure being unstable is, are all the reactions parallel? In this case, the answer is yes. And because all of the reactions are parallel, a lateral load, it's just going to go, okay? Another check for stability is, are all the reactions concurrent, okay? So in the case of this structure, does everybody see how all the reactions all meet at a common point? Does everybody see that? If I were to take this structure and just twist it, it would go. This structure is very akin to, like, if I had a bicycle and I turned it upside down and I was looking at the wheel. I could just turn the wheel would just go. I mean, the wheel can't move this way or that way, but it'll spin like crazy. This structure is unstable because it does not resist moment like that. It'll just go, okay? Does that make sense? So this structure is unstable because all the reactions are parallel. This structure is unstable because all the reactions are concurrent, independent of whatever the heck you calculate for I, okay? So that's what I meant when I say if I is positive or if I is 0, the structure should be determinate or indeterminate or whatever. But you got to check stability as well, okay? Does that make sense? Okay. Now, what does an equation of condition do? Again, it just ups your EC value. So this structure right here, this is a 3-span bridge, if you will. This structure would be indeterminate to the 2nd degree. But if I threw an internal hinge right here, suddenly it would be indeterminate to the 1st degree. And if I threw 2 internal hinges, this structure is stable and determinate. Okay? we'll learn how to solve structures like that throughout this semester. You know, so we'll spend some time on that a little bit later. Okay. Let me take a step back. How are we doing? Is this easy? Hoping this isn't all that complicated. So, any questions? Let's do some practice. Okay. So I threw some problems here. I'm going to pull them up here on the notebook. All right. And I'm going to make these structures, or these images, a little bit bigger. Make that a little bit bigger. Not that big. That's good. Whatever, it'll be fine. Okay. So let's look at example 1. Okay. So here's what I'm gonna do. I'm gonna walk you through the first example, and then I'm gonna start asking for a little bit more help as we go for the remaining examples. So let's start with example 1. So the first thing that I'm going to do is I'm going to start identifying the reaction forces that are going to be present on this structure. Okay. So by the way, whenever you're assessing whether or not a structure is stable or determinate or indeterminate, it is independent of whatever loads are on the structure. So notice how I'm giving you these problems and there's no loads on them. Because it doesn't matter what the loads are in terms of assessing its stability or its determinacy. That doesn't matter. Because the idea is that if a structure is stable, no matter what loads you put on it, it'll respond, you know, in a stable fashion. So, okay. This first one, this is a pin. Well, first of all, they're all going to have vertical reactions, but this first one is a pin, so it's going to have a vertical reaction and it's going to have a horizontal reaction right there, right? So, 2 reactions here, 1 reaction here, 1 reaction here, okay? So, my R value is going to be 4. Okay? Can everybody see and read my handwriting right here? If you ever have any problems reading my handwriting, let me know. I will take it personally, but I will try and improve. So, this is a joke, not a funny one. Okay. Now, this first structure does not have any internal hinges, any internal releases. So, its E sub C is 0. So therefore, I use that 3 dot symbol quite a bit, so that means therefore. It's a shorthand for therefore. So therefore, I sub E is R minus E sub C plus 3, which is 4 minus 0 plus 3. Which equals 1, okay? And does this structure pass the stability test? Well, do we have a situation where all the reactions are parallel? No, because this reaction is not parallel with these. Do we have a situation where all the reactions are concurrent? No. These 2 meet at a common point, but these 2 don't, right? So does this structure pass the stability test? Yes. What is the I value? 1. So we would say that this structure is stable and statically determinate, or indeterminate, sorry, indeterminate. And we would say that is to the first degree. And we say that that's indeterminate to the first degree because I is 1. Does that make sense? Okay. Let's talk about example 2. So this one, I'm going to need a little bit of help from you. So, how many reactions here?
6.
6 total, right? Because there's how many here? And how many here? 3. Yeah. So we're going to have, for this one, a horizontal reaction, a vertical reaction, and a moment. here, here, and moment. And by the way, for this type of assessment, it doesn't matter if the vertical reactions are going up or going down. It doesn't matter if the horizontal reactions are going left, going right. It just matters that you've identified them as potential unknowns. That's what matters. So, for this example, R is 6. Now, somebody else help me out. What is E sub C going to be for this example? 3. Because there's 1, 2, 3 hinges. So those are 3 points on the structure where I know something about the internal forces. And what I know is that the internal moments are 0. Hinges correspond to internal moments. Okay? So in this case, therefore, IE would be 6 minus 3 plus 3, which in this case is 0. Now, does this structure pass the stability test? Yeah, the reactions are not all concurrent, they're not all parallel. So how would we classify this structure? Somebody tell me, how would we classify it?
Stable and statically determinate.
Exactly right. This is one of those things where you throw an image into ChatGPT and it says, oh, your structure's stable. Well, no, it's not, you know. That's kind of the whole point. All right, example 3. Tell me what's going on with example 3.
Big skateboard.
What's that?
Big skateboard.
Big skateboard.
Three-wheel skateboard.
This is a skateboard because we've got this, this, this. So, do I do any math? No, it's unstable. I do not care what the degree of indeterminacy is. I do not care what I is if the structure is unstable. And the reason is that if a structure falls down and kills somebody, nobody's going to care what the I value was. Do you know what I mean? Like, it doesn't matter. So, it's just unstable. Move on. You know what I mean? Okay. Now, this last one, I'm not going to do anything. I want you to do a little bit of work and then tell me what it is, and then we'll work through it together. I'm just going to sit here in silence for a second until somebody gives me an answer. Anybody have an answer for me?
Stable and statically indeterminate.
To what degree?
First.
First degree. So let's see. Oh. Oh. There we go. 1, 2, 3, 4, 5, 6. Passes the stability test because they're not all concurrent and they're not all parallel. And I think I counted 1, 2 hinges. So R is 6, E sub C is 2, I sub E is R minus, which is 6 minus, getting ahead of myself. 1, so stable and statically indeterminate. That's not too hard, is it? Okay. I know we're getting close on time. I'll just show you something real quick just for your homework. So your homework assignment, which is due Friday at 11, is to do this for 5 problems. Okay? Now, because I know you're waiting, some of you might be waiting on the textbook, I went ahead and put the images for those problems on the later page, but I want to be clear. Okay? So let's say, look at this. So this says textbook problem 3.1c, okay? I gave you, like, so the way the textbook is, this is 3.1, this is the whole problem, right? Don't do all of them, just do C, okay? Don't, there's only 5 of them. Don't do the whole thing. And so I'm going to do that for the first couple weeks or so while you're waiting on a textbook, but probably like post-Labor Day, I'm not going to do that, okay? Does that make sense? I'll bring up the code one more time, everybody. I'll see you on Friday.